Welcome to Voice Bootcamp. Hello, my name is Faisal Khan, and I am the Cisco instructor at voicebootcamp.com. In this video series of CCNP and CCIE Enterprise Cisco ENCOR course, which is implementing operating Cisco Enterprise Network core technologies. Cisco ENCOR is one of the fundamental requirement or foundation requirement for anyone who wants to achieve their CCNP Enterprise or CCIE Enterprise designations. This is one of the mandatory courses that you must have in order to achieve your certification path. Now, in this particular course, you're going to learn about networking skills, and you're going to learn about technologies that are used by Cisco to build from a very basic to very sophisticated infrastructure. The chapter will be divided into two areas. First, we're going to talk about the network device communications and forwarding architecture. The network device communications will focus on switches and routers and how each will route traffic based on their OSI layer perspective, such as switch operating at layer 2, whereas routing will operate at layer 3 infrastructure. We'll also look at forwarding architecture. How does these two devices route or forward traffic based on various mechanisms that are available, such as Cisco Express forwarding? Now, the primary function of any network device obviously is to provide some sort of connectivity. Now, you have a switch which can provide connectivity, so as the router does, but their purposes may be different. There used to be a variety of network protocol that were used during in the older days that are very device specific. Today, however, pretty much everything is running on a single protocol that we need to be very good at. That is called the TCP/IP, or short form Transmission Control Protocol / IP Internet Protocol. Now, it is important to note that TCP is based on a conceptual open system interconnect or OSI model that is composed of 7 different layers. Now, we'll talk about those layers in the subsequent chapters. Now, each layer will describe a very specific functions. From the moment you press www.google.com, traffic will go from your PC or your handheld device into the network through those 7 layers of communications. Now, when the traffic goes into other destination, it will then reach back to the destination in a very similar layer, and whatever happens in a layer 1 on your side will take place on the layer 1 on the other side as well, and so from layer 2, layer 3, layer 4. Each layer plays a vital role. Now, there are 7 layers in the OSI model. Now, this is something that you should have a good understanding if you want to be part of your if you want the networking to be part of your day-to-day job. Now, the OSI model, which provides a structured approach for compatibility between different vendors, as for example illustrated right here. These layers are divided into 2. You got the media portion and you got the host portion. Layer 1 to layer 3 are considered to be the media portion. This is where you are involving with the cables or the wireless signals or the switches or the routers, etc., etc. When you think about flow of your data, such as when you're trying to go to www.google.com, the most network traffic will involve communication of the data between different applications. For example, if I'm trying to browse a Google web page, I'm going to use Google Chrome. Google Chrome is a part of an application that resides on one site, and it's trying to communicate with an application that is residing on the destination. If I'm trying to reach www.google.com, I'm going to probably most likely use Google Chrome to access a web server residing in the data center managed and hosted by the Google data infrastructure team. Now, the application layer that will generate the data at a layer number 7. So this is where the Google Chrome will be running at layer 7. So whenever you open the Google Chrome, or let's say an email Outlook or some sort of application that communicates with someone else, you're basically gonna first communicate at layer number 7. That is often known as the application layer. The device and host, such as the computers, Android PC, or anything that you might have that you want to use to browse your internet, will then send the data down through these layers all the way to the physical layer. as the data moves down to the OSI layer, it is encapsulated with information that is represented of that particular layer. Now at layer number 3, which is very common that we, especially for our routing switching individual, at layer number 3, the device or the host, in this case could be your handle device, could be your fridge, could be your Apple Watch, whatever that it may be, will decide whether the data that needs to be sent to another application on the same device or not. Because sometimes you may want to send data within your own computers, so you don't need to communicate with the network, right? So layer 3 will decide, am I sending this information to myself or to someone else? Then it would then start moving the data from that particular stack, from layer number 7 to the layer 6, 5, 4, all the way down through the network. Of course, if the data needs to be sent to different device, the device or the host, which is sending the data, will continue processing down the layer from layer 7 to all the way to layer number 1. Now, the layer number 1, which is responsible for transmitting the information onto the media. In this case, the media could be the cable, could be your DSL connections, could be your radio web, could be your Ethernet connections, whatever the internet connections that you might have. Now, if you are using a home computer, most likely you're going to use an Ethernet cable connected to your local hub or switch or the modem provided by your ISP. But if you're using an Apple Watch, or if you're using a handheld device like your cell phone or mobile phone, then you're going to probably use some sort of wave, like wireless wave. On the receiving side, the other side of the network, they will receive the data on the layer number 1. It's because it's going from the physical layer or wireless into the other device. The first thing that it hits on that other device or the destination is going to be the layer number 1. Now, as it receives at the layer number 1, then it will move all the way to the layer number 2 and so until the data is moved up to layer number 7. That is when the other side will see the data on their end or response to the data as per the instruction of the applications. Now, this chapter basically reinforces the concept related to how a network device will forward the traffic either from a layer 2 or layer 3 device perspective. So the first layer 2 network device were basically the bridge or the switches, or sometimes even call it a hub. Layer 3 device, on the other hand, are strictly the routers. Now, sometimes these two devices could be a single device, or usually in an enterprise, they're separated, depending on whether you are in a certain edge of your network. Now, the first, as the technology advanced, the development of a more faster physical media required the ability to forward packet in a hardware through what we know as the ASIC chip, or basically an advanced chip mechanism. An ASIC functionality will continue to develop. A multi-layer switch were invented in order to forward your layer 2 traffic in a hardware as if they were switches. However, they can also perform other functions such as routing packets or from a layer 3 perspective. So typically at the very beginning of our internet journey or network journey, we used to use a concept called hub. Now the hub was basically a multi-connector devices where your computers will be connected to it. But the problem with the hub was mostly driven by software processing. And because the hub was more of a software processing, when a computer X sends a traffic to the hub, most likely the hub is going to share that bandwidth with the rest of the other PCs. If too many PCs are sending traffic to the network, your hub can become a congestion point. So the industry or technology, as it improved, they start to use new functions based on hardware switching or forwarding packet based on the hardware. That is called the ASIC chips, which is basically advanced chip where your hub is now become what we know is switches. Switch is basically designed to give you a port level speed. So if your port is 100 meg port, you'll get 100 meg speed on that particular port. If your port is 1 gig, you'll get pretty much close to 1 gig. Whereas a hub if you were 10 gig or 100 gig, chances are that all port may not be able to enforce the entire bandwidth because it's a shared devices. So therefore, it will be sharing the bandwidth with every other port. So chances are that if one of the port is 10 gig and other port is 100 gig, chances are that 100 gig port never really utilize full 100 gig or 100 meg, for example. Now, the second layer of the OSI model, which is called the data link layer. Now, this is the layer that is responsible for basically providing or handling the address for that physical device. Now, one of the things about in internet or even networking, every network device, every peripheral or gadget that you have that's going to communicate with some sort of form of network is going to need a unique address. And that unique address is called the MAC address, often known as Media Access Control. The MAC address will be running on layer 2. Now, these MAC addresses are very unique, meaning that no two devices in a world that you can buy will have the same MAC address. Now, can they be spoofed? Sure, but that's another argument. Now, the other data link layer protocols, such as, if you're using other than frame Ethernet, like you could be using frame relay, or which is pretty much doesn't exist anymore. If you do use those technology, they will also be running on a layer 2 addressing mechanism as well. Now, the focus of this enterprise core exam or ENCOR is to focus on the Ethernet and the wireless technology. There's no more frame relay, there is no X25, there's no token ring anymore. That means some companies somewhere in mining area might still be using frame relay, but the core of this particular video will be focusing on the either Ethernet or your wireless technology. Now, this chapter will focus on the MAC address from layer 2 forwarding perspective. So what is a MAC address? A MAC address is a 48-bit address that is split into 6 octet. Like you can say A dot B dot C. So you're dividing that into 6 different octet noted in a hexadecimal. Now, they'll be like this, a group of 2 into total of 6. Now, first 3 octet are assigned to the device manufacturing. So usually what happens is this first 3 octet that you're seeing, they're basically designated for a company. So, for example, all the network device or gadget that Cisco generate, the first 3 octet will always be the same for all those devices. So if you ever look at Cisco routers or switches and you look at their MAC address, you'll see the first 3 octet of those 6 octet are always going to be the same. Now, the remaining will be obviously used in various combinations to create the unique address for that particular devices. Now, it is possible that some company may have more than one group of MAC address. Certainly possible, because you may have a possibility of running out, right? So the first 3 octet, as I mentioned, refer to the device manufacturer, which is known as the Organizational Unique Identifier, or known as OUI. The manufacturer, of course, is responsible for ensuring that the last 3 octet, which is right here, will be used uniquely across the entire organizations. Now, what happens if you run out of it? Most likely you're going to have to get a new set of MAC addresses. Now, a device that listens for network traffic will often contain this MAC address as part of your destination packet. So what do I mean by that? So let's say if PCA wants to send the traffic to PCB, so part of your addressing mechanism is that the sending device will have the MAC address of the destination device. May not be the final destination, but the next destination device MAC address in its packets. Now, often a device will listen for network traffic that contains this MAC address as its packet's destination's MAC address before packet move from the one layer to the next layer, in this case, layer number 3 or layer number 1. Network broadcasts with a MAC address such as all F. So this is the special MAC address all 6 octet of apps. This represents a network broadcast address. Now, there could be certain exceptions that sometimes different depending on how your subnets are configured, your network broadcast address could be slightly different. Now, broadcasts are not typically forwarded beyond the router or layer 3. So if you're sending traffic on layer 1, layer 2, layer 3, broadcast will never cross beyond that layer 3 devices. Now we'll talk about that when we talk about the routing perspective. Now, in this particular figure, you look at for example, we have a switch where 4 devices connected. A switch will usually build a dynamic table known as the MAC address table. Now, which will correlate the local PC to the appropriate switch port. So what it does, it shows you that this MAC address is connected to this particular port. So when you look at this port and you see that this is the MAC address of this particular PC that is directly connected to it. So when a PCD, for example, wants to send a traffic to PCA, one of the first things that PCD is going to try to do is resolve that IP address or the destination address of PCA into the respective MAC address. And switch will then look at, so look, yeah, I know that MAC address. It's right here, and I have this entry, so that next all you have to do is for the traffic to that interface in order to reach the PCA. This table is dynamically built in most scenarios, but of course you can also manually configure it if you require to do so. Now this is basically the MAC address table. Now some switches, they may call it a CAM table, some switches just call it a MAC address table, depending on which version of the switches that you have. Now, when you have a big switch, so for example, if I look at a switch right here, this is considered to be by default one physical network. You got a switch, you got devices connected to the switch, and everything is working fine. It's considered to be one network. Now that is called usually the network number 1, or sometimes we call it a VLAN. Now, sometimes we may need to divide this network into smaller pieces. Okay, so sometimes we take this large local area network and we want to logically divide them or partition them. This is called the LAN segmentations. And in order for us to do that, we take a big switch, whatever they may have, however many ports that you might have, and each one of these ports can be allocated into different partitions. And that partition is often known as the VLAN, Virtual Local Area Network. Virtual Local Area Network is logical segmentation by creating a multiple domain within your same network. You see, when you have a switch, a physical switch with a bunch of ports, the entire switch is called a single broadcast domain. If a PC here sends a traffic, chances are that every other PC will get to see that traffic within the network because of the nature of broadcasting. So to manage our network, so that if you have a 5,000 employee or 10,000 employee, you don't want one person sending a broadcast and all 5,000 get to see that. It makes no sense because that person may not really need to reach all those 5,000 people. So what do? You decide to segment the network. You say, okay, I'm going to divide the port into different group, partitioning it. So anything, maybe I want to define it based on my department, sales VLAN, support VLAN, management VLAN. So that if something happens on the management V network, it does not affect the people in the sales team, or it does not affect the computers in the IT department. We could do that by taking the entire switch and logically partitioning it. Now, of course, I can always buy a separate physical switch and isolate them, but that will go against my cost. It's not going to be cost-effective solutions. So Cisco, the concept of VLAN basically provides a higher utilization of your switch port because a port can now be associated with the necessary broadcast domain. That means if I were to go back into my previous design, so let's say I have a switch here and I have 2 ports, and I decided that between there will be a VLAN X here and VLAN Y. So in this case, VLAN X has two computers, VLAN Y has one computer or one port. So whatever happens to this particular port X, well, VLAN port number Y may be able to see that information, or will be able to communicate successfully. But VLAN A, for example, switch port A, or port A rather, is not going to be see those traffic, because that traffic is in different VLAN. Now, by default, every single Cisco switch port has or part of VLAN number 1. You cannot delete that particular VLAN number 1, but you can create more. As you create those VLAN, you have to then decide which port goes to which VLAN. So it is possible that you can you can configure each individual port to be member of one or multiple, one VLAN. Now, the VLANs are defined by an organization known as IEEE, and the standard for that is called 802.1q. Now, the 802.1q, which basically is a 32-bit that are added to your packet header. So you'll see that there is a 32-bit field being added to your packet header, and each field provides different functionality. So first of all, the first field that you have in the header, of course, you got your destination MAC address, you got your source MAC address. So if I am sending traffic to you, my MAC address will be part of the source, and your MAC address will be part of the destination MAC address. Again, the MAC address being the unique hardware address for the network devices. It could be your fridge, it could be your car, it could be your Apple Watch. Now, the remaining 32-bit, which is coming from your header, contains TP-ID, PCP, DEI, and VLAN ID. The TP-ID, which is a 16-bit that is used, that field is set to 0x8100 code, which is to identify the packet as being 802.1q packet. So when you see the packet with this label, that means this packet is a 802.1q packet. Right away you can look at, and you can always look at that information in your packet trace in your trace files. Then the PCP stands for, is a 3-bit that indicates the class of service as a part of layer 2 QoS. So if you have configured class of service or QoS configuration, the PCP bit will be set accordingly to that. Now, you will learn about QoS later in the course, where you will see what those class of service basically means. Then you have something called drop eligible indicator. It's a 1-bit, and that bit will indicate whether the packet can be dropped when there is a bandwidth contention. So sometimes when a packet goes out to the network, you might say certain type of packet should be eligible to be dropped if there is a congestion in the network. So when a congestion happens, you need to make sure that the priority traffic is passed through first, but at some point you may have to make a decision, I have to drop certain packet. Well, which one? Well, that will depend on if that particular bit is set for that particular packet. If the bit is set, therefore that packet will be candidate for dropping should there be required. Not just because you set the packet to be enabled, it doesn't mean the packet will be dropped. The marking has to be done at somewhere to take that actions. VLAN identifier has only 12 bits. Okay, so the last one is called the VLAN identifier, VLAN ID. It's a 12-bit field that specifies the VLAN that is associated with that packet. So if I am sending packet to the network, so let's say I got PC here, and in this scenario, my computer is connected to this port A, and I am going to send traffic to the network. What I'm going to do is that particular bit, VLAN ID, I'm going to set to number 12. That means I am using VLAN number 12. Now, it could be 1, it could be 2, could be 3, could be 100, depending on what is your VLAN ID. The VLAN identifier has 12 bits, which provides 4094 unique VLAN information. Now, the catalyst switches will use some of the logic for your VLAN identifier. First of all, VLAN 0 is reserved for 802.p traffic and it cannot be modified nor it can be deleted. Then you have VLAN number 1. Now, VLAN number 1 is the default VLAN. You cannot modify nor you can delete, and by default, all the port in your switch are automatically part of VLAN number 1. That is unique. That is something that you can't remove. Now, VLAN 2 to, so then you get 2 to 1001. These are the normal VLAN range and can be added, deleted, modified as necessary. Then you have something called VLAN 1002 to 1005. Now, 1002 to 1005 are reserved and cannot be deleted from your switch. Last but not least, you got VLAN 1006 to 4094 are again extended VLAN range, normal, and can be added, deleted, modified as necessary. You cannot go to below VLAN 99, VLAN 40 because that is not going to be supported. So maximum is up to 4,900 and 4,094 address VLANs IDs, and those ID will be part of your VLAN ID. How do I create a VLAN in a switch? Pretty straightforward. You go to your switch and then you type the command VLAN 10 and you define a name, etc. Now, I'm going to show you how to do that on a Cisco switch by logging into our Cisco dCloud access. So here you can see that I have a network of 3 switches, switch 1, switch 2, switch 3, R1 and R2. And I want to assign the PC1 and R1 into one VLAN number 10. So first, remember what I said, that all these port 0/1, 0/0 are connected right now to VLAN number 1. So let's go into the switch. So what I'm going to do is first type to see how many VLANs I have created, I have available. I'm going to type show VLAN. Show VLAN will show you all the VLAN that I mentioned right now. Remember what I said, VLAN 1 is special VLAN, cannot be deleted, cannot be modified, but it is assigned to all the port by default. Now this is a 4-port switch. Of course, you can have more port. This is just to show you the example. They're automatically available in VLAN number 1. Now I did create a VLAN number 2 if I want to assign it to VLAN 2, or I can create a new VLAN. VLAN 102 to 105, these are reserved, as I mentioned, cannot be used, but anything above VLAN 106 to 4094 will be extended VLAN. Now, let's say I want to create 2 VLAN, and I want to say that my voice VLAN, data VLAN is going to be 10, and I want to use another VLAN for voice. So I will go to, let me increase the font size. So I'm going to type config T and I'm going to type the command VLAN 1 or VLAN 10. VLAN 10. Remember what I said, the VLAN 10 is going to be my data VLAN and VLAN 20 is going to be my voice VLAN. So I'm going to name as data VLAN. Exit, and then you're going to type VLAN 20 and I'm going to call this name voice VLAN. So if you have a Cisco phone associated with your switch port, you can assign the voice port VLAN to that particular phone. So to show you the command show VLAN, you will see I now have VLAN 10 and VLAN 20 configured as per the requirement. Okay, so by creating the VLAN itself is not enough. You need to assign it to the port. And as you can see from the switch number 3, is connected to VLAN 0/0, sorry, port 0/0 toward the router 1 and 0/1 toward the router number, PC1. So what I'm going to do is I'm going to assign the VLAN 10 to both of these ports and voice VLAN to both of these ports as well. So interface gigabit 0/1, which is going toward the PC. I'm going to start with that and I'm going to say switch access VLAN and it's going to be VLAN number 10. And that's how you assign data VLAN to a particular port. Now, if I want to configure voice VLAN on that port, because I'm going to assume that there's a PC, there's a phone connected to that. Behind the phone, there is a PC. If that is the case, then I will say switch port voice VLAN and then the voice VLAN ID. In my case, the voice VLAN ID was set to 20. So that's basically how you create the VLAN and assign it to a port. Now, remember in the router side, I'm going to configure only the access VLAN, which is 10, because the router does not have any phone associated with it. So right now, if I want to type the command show run, so here we'll see my port assigned to appropriate VLAN. Now keep in mind, this particular router may be required to configure such a way so that it does carry traffic for both VLAN 10 and VLAN 20. And if that is the case, then the port that is connected to the router 1 has to be a special port. Now, by default, all the switch port in my switch is considered to be an access port. So access port is a port that carries a single VLAN at a time. So if I want to carry multiple VLAN, then that port must be a trunk port. Now we'll talk about what trunk is in a subsequent chapter. So you can see that how I've created the VLAN, how I have assigned the name, and then of course the associated with your port. Now there are some show commands you can type in order to get information about your VLAN by typing the show VLAN command, which will give you information about the brief summary, the VLAN ID, and of course any naming convention. Now, once that is done, like I said, most network devices network ports are considered to be access port. So access port are the fundamental building block of your managed switch. An access port is assigned only one VLAN at a time. It can carry traffic from a specific VLAN to another device connected to or from another device that it happens to be in the same VLAN as well. Now, the 802.1q tags are not included in your packet transmitted or received on an access port. So if the port is access port, it usually does not include the 802.1q tagging. A catalyst switch places the switch port as a layer 2 access port on VLAN 1 by default, as I mentioned. VLAN is associated to a port with the command switch port access VLAN command, like the way I have shown you in the configurations. So in this case, this particular port belongs to VLAN number 99, and the port is considered to be accessed by default. But sometimes you don't want to take that chance. So you say, you know what if I want to hard code the port to be an access port? So what you want to do, you want to, let's say, going to the PC port, which is interface gigabit 0/1. I'm going to say switch port mode, and there are four possible mode of a particular port. It could be an access port, could be a trunk, could be a .1q tunnel, and various other options. We're going to stick to access port at this moment. If I want the port to carry multiple VLAN, I'm going to make it a trunk port. Okay, so that's how you enable the port to be either access or a trunk port. Now, the trunk port is very important if you are going to carry multiple VLAN. So because the switch, you may have, let's say, if I were to configure this switch and I say I'm going to add another PC into my network, but that PC is going to be in a different VLAN. So I want that PC to be VLAN number 20. Well, if that is the case, then the router 1 has to carry traffic for VLAN 10 and VLAN 20. So in order to make that happen, what we want to do is we want to make sure this link between the switch 3 and the router 1 happens to be a trunk port. So I will go to the port of that switch, which is gigabit 0/0, and I'm going to say switch port mode trunk. This will make the port trunk. But when you enable a port trunk, it has to enable certain encapsulation. Okay, so we're gonna have to type a command switch port trunk encapsulation, and you got three choices: .1q, ISL, or negotiate. .1Q is the industry standard. ISL is a Cisco proprietary encapsulations. So we're going to say .1Q because we're going to use the industry standard tagging mechanism to understand multiple VLAN tags. And then we're going to enable switch mode trunk, and now the port becomes a trunk port. So trunk port by nature allows you to carry multiple VLAN. So if I type show interface gigabit 0/1, which is the port going toward the PC, and then I type show switch port, what you're going to see is that information about the VLAN port. You can see the port is enabled, of course, is a static access. The mode is access, is trunking is not set, is negotiated by default. And you can see which VLAN access mode belongs to, what is your native VLAN if your trunking was enabled, and so and so. And the voice VLAN is set.